Today on The Future of Everything, the future of flocking and swarming. Now, anyone who has ever seen a flock of birds in flight has likely been impressed with the beauty and the coordination of the birds. As they move, they turn in the air, they do these maneuvers that are just quite spectacular, and we all look at this and I think we all say, how does that happen? How are they dividing and then rejoining? How are they making turns? Is there a head bird, as it were? Is there a head bird making all the calls? Or do they in some way watch all the birds around them and take cues from them? Is there a plan, or is this totally spontaneous? Now, I've always assumed that the positions of the birds are determined, at least in part, by what I would think of as optimal aerodynamics. If you've ever been on a bicycle, you know that if you get behind somebody who's pushing the air out of the way, it is a lot easier to cycle than if you're having to be the one in the front. And so I assume that the birds position themselves in a way that is, in some sense, aerodynamically optimal. I actually have no idea if that's true, but I'm hoping to learn about that. Do the birds take turns at the front in order to distribute the responsibility, both for leadership about like where we're going, but also energy expenditure? I think the same questions might apply to schools of fish or swarms of insects. I think the details are probably very different, but the sense of wonder in watching them and seeing this amazing coordination of individuals is similar. In addition to the beauty of these phenomena, they also probably have practical utility. For example, will self-driving cars in the future fly in formation? Will they look more like birds, fish, insects, or maybe a herd of horses? Nick Ouellette is a professor of civil and environmental engineering at Stanford University. Nick studies the physics, energetics, and structure of flocks and swarms and related phenomena. Nick, why would a civil engineer study these phenomena? We might expect it to occur in a biology department. And what have you learned that may be useful in the context of engineering new systems?
Yeah, I get that question a lot. The fully honest answer is
this is what we're searching for on The Future of Everything.
I study these things because they're beautiful. Because they're ubiquitous, you see them all the time. And it's one of these, a lot of what motivates my research is you go outside, you look around you, you see something that's interesting, you think to yourself, gee, someone probably knows why this happens. And more often than not, when you do a little bit of reading, you find out that that's not the case. Yeah. That you only have to scratch the surface before you get to some kinds of what seem like basic questions where nobody really knows the answer. So that's the real full honest answer as to why I'm interested in these kinds of phenomena.
And your colleagues in engineering are okay with it.
My colleagues in engineering are wonderful. And in part, I think that's because it's very, very difficult in general to predict, 20 years down the line, what basic research now is going to lead to something really interesting in the future. That being said, I think there are compelling reasons why one may want to look at these kinds of phenomena from the standpoint of engineering.
Yes.
And it's part of a broader move over the past few decades towards bio-inspired engineering more generally, that you look to the natural world to see how evolution has solved problems. And if the same or similar problems show up in whatever you want to design, at least it's reasonable to ask the question as how nature has done this.
That's totally fair. So let me ask you, when you look at these flocks in their beautiful formations, what are the problems you see them solving?
And that is actually, in some ways, the most difficult question that we found to address in all of this work. Because at the end of the day, you cannot go and ask the birds, so why are you doing this? What's the purpose? You can make fairly reasonable arguments based on intuition from ecology. So interfacing with ecologists and biologists is really important here. In some contexts, so I should back up just a smidge and say that one of the hints that collective behavior, as this broad field is known, may be really valuable from an engineering standpoint is that you see this at every single scale in biology. That individual units or organisms work together to solve problems. Everything from single-celled organisms like bacteria, like cells, all the way up to whales. So you have literally the entire spectrum of biology that all cooperates to accomplish things.
And there is an idea that many of these are distributed in the sense that there is not a central boss.
Right.
And then that leads to a question about, well, how could you do that? Because so many human systems are hierarchical and do have a central, but not all human systems are like that.
But not all human systems, and in particular, not the systems that evolution has designed. So humans are much like birds or fish or insects in that we have collective crowding behavior all the time. So, and that especially kicks in when something is out of the ordinary enough that it shuts down our primary cognitive functions.
Right.
So if there's an emergency, if there's a disaster, and you're in a big crowded situation, I don't think any of us, if you think about it, you don't make rational decisions. You don't carefully weigh all the options. Should I put my left foot here? Should I put my right foot there? Should I go in which direction? You follow the crowd to get away as quickly as possible,
Right.
you think, from
Right.
whatever is going on.
Right.
So there are reasons to think that the kind of, and this gets back to the question of why would a civil engineer want to do this?
Right.
There's good reasons to think that things that we learn about how collective groups behave and how they can be manipulated may have may be able to be valuably mapped onto questions about crowd control, about the design of public spaces to avoid instabilities of crowding behavior that leads to events like trampling
Yes.
or dangerous situations.
Great. So before we get to those engineering applications, I do want to go back to the birds because I do really actually want to ask you the questions to these questions that I raised. So in fact, is there a head bird? And how do they do the leadership of these flocks?
Yeah. So the first thing to distinguish there, because the answer to everything is always it's complicated.
Right.
There are really two kinds of flocks you want to distinguish. And then we all have seen these.
Good.
So
We're
we
going to
all
have a taxonomy of flocks.
Right. The first kind, which kind of looks like it has a leader, though it probably doesn't, and where you may see aerodynamic benefits, are the kind of V formation
Yes.
flocks you see in large migratory birds.
Yes.
So geese, storks, ibis, all these kinds of things.
Very beautiful V shape
Very
with
beautiful.
sub-Vs. It's like fractal with Vs.
Yeah. So that's not what we have worked on so
Okay.
much. So I know that literature anecdotally, but I haven't worked on that myself.
In general, are they aerodynamically pretty good?
Yes, although it's complicated. So everybody wants to make the analogy to bikers.
Bikers. That's what I did
or
myself.
trucks on the highway.
Yep.
So trucks will do the same kind of thing. In fact, Ardeen, one of the most recent papers I published on this asked me that very question with cycling as a
Yes.
sort of touchstone. The difference really comes into the fact about how the birds are moving. And what's easy to forget is that birds don't just keep their wings fixed and glide,
Yeah.
they flap.
Right.
And so the way aerodynamic drag works on a flapping wing as opposed to a fixed wing is very different.
Yes.
So you can get aerodynamic savings, and in fact, it's been shown that these birds do get aerodynamic savings. But the key thing there is actually the phase of the wing beats down the V chain.
Right.
So you have to
Right.
catch the updraft
Oh, that's a beautiful thing.
from the bird in front of you, and then you get a boost from it. But if you're flapping at the wrong time, then you want to go up, and the vortex shed from the bird in front of you is going down, and then it's bad
Right.
for you.
So this is going to be slightly different principles than what the Blue Angels use because
Right.
they're all fixed wings.
They're all fixed wing, and so drag works differently.
This is the future of everything. I'm Russ Altman. I'm speaking with Nick Ouellette about, well, the bird taxonomy. We just learned about Vs, but there's another important type of flock.
So now think about the last time you went to a city and you saw a bunch of pigeons flying around. Right? Pigeons will do this. Most birds, songbirds will do this. Starlings are the classic example that form massive flocks. In those kinds of situations, the flock itself is not as rigidly sort of constructed as a V. The bird position is sort of more random.
Yes.
What we have found, we and others have found in those kinds of flocks is that, in fact, it's aerodynamically bad in that the birds wind up expending more energy to participate in a flock than they would if they were flying on
And
their
they
own.
do look somewhat chaotic, just on a visual. Even though they're beautiful and coordinated, they seem to be making tighter turns
Yep.
and vortices and things like that look like they might, in fact, be more energetically expensive.
Yeah, and that is borne out by the data as well.
And those are the ones that you study.
Those are the ones that we study.
So paint me a picture now for how the laboratory look? What does it look like? What are the key tools that you guys use to make these studies?
So the first
It
thing,
must be cool technology.
yeah, and in fact, the technology is how I got into this in the first place. So the first thing to note on this front is that it's not in the laboratory. So Stanford is a wealthy university. They give you nice lab space, all these kinds of things when you come. They don't give you enough lab space to have a few thousand birds flying around in free space. So this is very much a field project.
Okay.
So I have a wonderful collaborator in England, in Cornwall, who has been studying the native jackdaw population. So jackdaws are a small crow species, very social.
And I've heard crows are very smart.
Crows are very smart.
Which might confound your science, but we'll get to that later.
Well, people are nominally smart too, right? And so that's
well put.
And that's actually an interesting thing to ask about, how does intelligence map onto this ubiquitous biological phenomenon, where animals and organisms that are not very smart do similar things that look similar to animals that we consider to be very smart. But so this is not a project that's done in the laboratory. It's a project that's done outside. That's part of the reason why we haven't focused on the V-formation flocks. So the technology we use here is in principle fairly straightforward. We just use camera imaging to watch where the birds are going. So the simplest kind of thing you would do is you go and take a camera, you point it at the sky, you see a bird flock flying around, and you take some pictures.
And it would be a movie,
It'd be
presumably.
a movie, yeah.
But that's 2D.
That's 2D, and there's only so much you can tell from a two-dimensional projection of what the birds are doing. So what we actually want to do is to measure them in 3D. We want to be able to locate in three-dimensional space where all the birds are, how they're moving, and as much other detail as we can get. So the way we accomplish this is similar to the way we see in 3 dimensions all the time, which is to use more than one imaging device. So we have 2 eyes, and that allows us, with some neural processing, to reconstruct a picture of the 3D world. We do the same thing with multiple cameras.
And then these flocks, I presume they are absolutely freely behaving. There's no training. There's no
training.
And you don't physically even limit them, do
Nope.
you? And so it's catch as catch can in some sense.
And this is why having a collaborator who has spent decades mapping out the behavior of these birds is vital to this project. Because the first thing you learn when you go to do field work to try to look at the sky to see birds is that there is a lot of sky and birds are very small.
Exactly.
So if you just randomly pick a spot and put some cameras out, the chances of seeing a good bird flock flying over that is 0.
This is the future of everything. I'm Russ Altman. I'm speaking with Nick Ouellette now about studying birds in the wild with 3D capabilities. What do we learn? I mean, I'm sure people have been dying to hear. What are the kinds of things? Where is the science now in terms of understanding the coordination and distributed decision-making of these flocks?
So there's a number of things that people have learned about this. So the first large-scale experiments, quantitative measuring birds, were with starling flocks from a group in Rome. And they found a number of very interesting things. So there's been a supposition in the field for a long time that it's reasonable to expect that if you're a bird in a flock and it's a dense flock, and there's, say, thousands of birds, there's no way that you know what everybody else is doing. Just not a chance. Which means that all of the coordination you see has to come out of decisions you as an individual make based on information from your local neighborhood.
Yep.
But one of the questions is, well, what defines that neighborhood? Is it that there's a distance in space that you can see, 5 meters, and you just look at everyone there?
These are the questions that were, as I was writing my introduction, I said, I have no idea what the answer to these questions are.
The other way that you could think of defining what does a neighborhood mean is that you pay attention to some number of other birds. Mm-hmm. And it doesn't really matter if they're 5 meters, 10 meters, 2 meters away from you. You pick, say, 8.
Right.
And then you follow that motion. There's good reason to think that that's biologically more reasonable because you don't get then overloaded if the flock gets denser. Mm-hmm. And in fact, with the starlings, that's what was found.
And so how do you prove something like that, right?
It's a very difficult
So you have a model that, okay, the bird is either looking at one or two birds in front of him or an assembly of birds around them. I guess that leads to specifically testable hypotheses?
Yes. So the way we do this is to make the hypothesis that if reliably you are paying attention to other birds at some distance away from you, either whether that be a counting distance or a distance in space. There's probably going to be some spots you'd like to position yourself relative to those others that are preferable. You want to be able to keep them in view. Maybe you want the aerodynamics to be not terrible.
Right.
So there's going to be some statistical bias. So what you do here is to get an estimate of range, you see how far away do I have to push that range away from me before the statistics look uniform in space.
Yes. So that's good. And that allows you to conclude that there's like a set of birds around, maybe not even the few closest, but they're a little bit more complicated than that this bird, is there indeed, you made a vague reference to this a moment ago, is there also an awareness of the, I guess the aerodynamic, the pressure environment around the bird, like the aerodynamics, I'm sensing turbulence here, I'm sensing smooth air over there, or is there no evidence for that?
Honestly, we don't know because we can now, you got to imagine that the birds, when you have a camera on the ground, you're looking at a flock in the air, so it's very far away from you. So at this point, we can measure what the birds are doing, but we don't have a local measurement of the fluid flow around them.
Right.
My guess is that the answer is probably no, that they don't pay that much attention to it on average because the statistics you see don't seem to matter sort of where you are in the flock, if you're at the front, if you're at the back, if you're on the sides, and the fluid mechanics environment will be different in all of those cases.
Yes, that makes sense.
So if the aerodynamics is a player, it does not appear to be a primary player in this.
So I know that a part of your work involves simulation. So you go back to the lab, to the regular lab, the not beautiful Cornwall. I'm going into a reverie thinking about what it must be like out there.
Well, it's December.
Oh. Okay,
that's when they do what we want them to do.
Reverie.
Yeah.
But let me ask, when you get back to the lab, what kind of simulations are you doing, and how does that inform what you do next time you're in the field?
Yeah, so the simulations are a lovely place to test hypotheses. So you can build a little model that says, okay, suppose we think that a bird pays attention to 7 or 8 of its neighbors, or it pays attention to everything in some distance. You can put those rules into a computer and simulate what you would get, and then try to look in those two simulations where you know what you put in. You never know with the birds. You don't know what they're doing.
Right.
But you know exactly what you put on the computer, and then you can see what the output looks like.
And if it matches the behaviors. So that actually, okay, this is kind of a random question, but has the cinema industry approached you about getting better fidelity CGI simulations of bird flocks?
So they haven't approached me because this has been done in the cinema industry since the 80s.
Oh, so they're pretty clueful about birds.
Mm-hmm. So actually one of the real seminal papers in this field was written for the Computer Science SIGGRAPH conference in 1987 by a wonderful person who actually lives in Mountain View, just down the road. So it's a classic paper, and it's been used in actual feature films since the early 90s, if not before, and in the video game industry as well.
Now, are those things of interest to you, or are they in some way cheating in a way that it doesn't give you the insight you'd like?
It's not cheating, but I will say that we haven't focused on it too much, because one of the things that you start to learn when you do lots of different simulations is that many, many different sets of rules give you a visual output that looks very reasonable.
So they may have set upon something that gives you a perfectly good-looking movie, but not related to the actual mechanisms used by the birds.
And this gets back to the context, the engineering context in which I'm working. If at the end of the day I want to have, I learn what the birds are doing and then potentially apply that to an engineering problem and say evolution means that this is probably good, if I understand what it's being optimized for, I need to be pretty sure that I got it right.
A perfect segue to our next segment. This is The Future of Everything. I'm Russ Altman. More with Nick Ouellette about birds, but now the engineering implications of all these learnings next on Sirius XM. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Nick Ouellette about swarming, flocking. We've been talking about the study of birds and their flocking capabilities, but we promised to get back to the engineering applications of these ideas. So Nick, paint a picture for me about how some of these learnings are either directly useful or leading to useful information.
Yeah, and there's a couple of, so I should preface this by saying that we're still sort of in the discovery phase of this kind of research, so I haven't personally spent a lot of time on the application side. But two areas that I think are probably the most promising to apply this kind of work in engineering. One is on the question of human crowds, either crowd control or the design of spaces to manipulate crowds in a passive way, and on the control of distributed systems more generally.
Mm-hmm.
So if you take the second of those, for example, more and more in...
And define distributed systems for people who might not think about them every day.
So in some sense, a traditional way of doing engineering, if you think about how you control something, you build a system that's sort of one big monolithic thing. So take the powering. One of the other things that we work on in the lab is questions about how you might want to design next generation power systems or electricity systems for cities. So, standard old design is you build one big power plant and it pipes all the electricity to the city, you're fine. Well, these days, with the development of lots of local renewables, you could do that still, or you could put a solar panel on everybody's roof, or you could do anything in between. So those would be examples of distributed systems where you have many, many, many components to the system that all need to interact. But as an engineer, you still need to have that system be controlled. It should do what you want it to do. It shouldn't fail. It should be robust, all these kinds of nice things. Traditional engineering control work is a very top-down kind of thing. You want to know what is the total information in the system? What is everything doing? And then make decisions based on that.
Right.
As we were just arguing, the birds or animals don't do that. A single bird doesn't know what all the other birds are doing. And yet the flock itself is very coherent and very consistent in its behavior. So this suggests that there's an alternative paradigm where you use only local information with local interactions that are of the right type, such that the entire system still has functionality and is very, very robust.
Gotcha.
And that I would argue that kind of bottom-up control scheme should at least be on the table as engineers we move more and more toward thinking about distributed systems rather than monolithic systems.
And are you thinking about distributed systems like self-driving cars and trucks? Or
Absolutely.
Is there a particular, or from your perspective, are they all about the same?
Well, that's a good question. I would say there are aspects to all of these things that are about the same. Once you, and this goes back to your question about what do you learn by putting things on the computer in a model, in some sense, once you've abstracted the real system into a model and you've validated the model, well, now it's just math. And anything you can apply that math to, so any different mapping, you have a variable in your model and it came from meeting a bird, and now it means a car, doesn't really matter from the math standpoint.
Now, but let me ask, because you've mentioned, two things have come up in our conversation: humans and smart crows. And they have social structures. So does that matter?
That, I think, is actually a very, very interesting thing. And this is where a lot of the recent work we've been doing with animals, where we've been focusing. So the answer to that question, even a couple of years ago, was not known. So, you can definitely say that humans have sort of social interactions. Does that matter in a crowd situation? One of the reasons why I was excited to work on jackdaws is that unlike what we think about starlings, the biology is always difficult. We know that jackdaws and other crow species have very intricate social systems. And for jackdaws in particular, we know that they mate for life. So you have a society that's built of these mated pairs. In the roosting season, in the winter months in England, where there's no young in the nest, both members of that pair are free to fly around all day. So when they form these flocks, anecdotally, people had seen these and seen, it looks like that flock is composed of lots of little pairs of birds.
And you can see the pair behavior in the flock.
You can see the pair behavior in the flock. And we can pick that out automatically. So once we get our data set, we've imaged the flocks in 3D, we know where all the birds are, you can actually pick out which ones are paired together.
And it's something like these two maintain a close distance over a long period of time, which allows us to infer that they're spouses. I don't know if that's the right word.
Partners, we'll say.
Partners, thank you.
And they also maintain similar configurations over time. So the placement of each bird relative to each other is also fairly consistent. So there's a lot of statistical measures we can throw at this to determine what those pairs are. And then you can start to ask the question, okay, great, you found pairs. Does it matter from the standpoint of the flock that there is structure on the inside? And the answer, in some sense, surprising answer to that is yes, it does. And what we found is that the more pairs you have in the flock as a percentage of the number of birds, because not all of the birds are
There's
pairs.
Some bachelors.
There's some singles.
Bachelorettes and whatever.
Whatever.
Forgive me, everybody.
the more pairs you have, the less responsive the whole flock is to perturbations from the outside world, things like predators.
This is the future of everything. I'm Russ Altman. I'm speaking with Nick Ouellette, and we have just learned that the mating pairs, in this case, of these birds, actually affects the dynamics of the flock. So please.
So the more pairs you have, the overall flock is sort of not as effective at doing things like avoiding predators as it would be otherwise.
So it's a little bit of a negative.
A little bit of a negative for the society, for the group. But at the individual level, that is balanced by a couple of interesting savings. So what we've also found is, so I told you, okay, that the birds pay attention to some number of neighbors. Well, that number is smaller if you're part of a pair versus if you're not.
You're focused on your kin.
You're focused, well, it's typically about three or four. So definitely your partner and then a couple of others close to you. But but about half the range, half the number of birds you pay attention to if you're not part of a pair. And that has an implication back to the aerodynamics.
Right.
So what we found is that it's always an energetic hit. There's an energetic cost to being part of the flock, which is reasonable to pay if you get benefits like, a hawk comes by, it eats one of your neighbors instead of you. But that cost is mitigated at the local level if you're part of a pair. You're not paying attention to as many other birds, so it's more beneficial for you. But there's an individual level savings, but a global cost to the group.
And it's not hard for me to imagine similar dynamics in a crowd fleeing an emergency where your partner, you're keeping an eye on them.
Yep.
You are trying to save them if they're in a tough spot where otherwise nobody might try to save them. But that might lead to a less effective, emptying of the theater.
Or at least something you need to know about when you start to try to poke and prod at that and manipulate it. The other area where I think this might be interesting to think, if you think about self-driving car fleets and controlling them with these kinds of local rules, well, you got your Google cars and you got your Uber cars and you got all these other kinds of things. And even if on paper they're all supposed to be communicating in the same way, protocols may be slightly different. There may be asymmetries.
Right.
And what we've been finding in the birds is that those little local asymmetries can have consequences.
So now we have a potential. I'm not sure it's an engineering principle yet, but you're pushing close to a principle that we may want to evaluate the costs and benefits of having different algorithms on the different cars, because that may lead to a similar behavior as birds that are caring more about some birds than other birds.
Or at least it's something one should be aware of.
Yes.
As we move toward using these kinds of rules that we're learning from nature and applying them in engineering contexts.
So when will these principles affect people in the real world? When are we going? And I know it always takes time.
Always takes time.
But give me a sequence of events that might lead to these principles affecting the systems that are being built.
That's a question I probably can't answer. I don't know that I want to speculate too much.
Please do. We're in the last 30 seconds.
Yeah. If I had to guess, I would guess that it's going to be in the crowd control arena that you're first going to start seeing things like this, because there's a longer because we've known about crowds a lot longer than self-driving cars.
So human crowds.
I would guess that there's going to be...
And perhaps the way that they set up exits, the way that they engineer buildings for entrance and exit.
This is already something people are thinking about. As we get more data, I think we'll see...
And that's actually exciting for improved public safety.
Absolutely.
There are cities. The cities are crowded. Fantastic. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.